So, hello, welcome to another episode of Beam There, Done That. I'm your host, Alan Wyma, and today we have, of course, my other host, Francesco Cesarini.
Hi, I'm Francesco. I'm also co-host. Welcome to the show. Today we will be tackling the question of how we bring, static types to Erlang and Elixir. It's a quest which, I tend to joke is almost as old as Erlang itself. And joining us are Annette Bieniusa and Guillaume Duboc. But before introducing them, let me go in and give you some background on the topic. When I was at the computer science lab, back in 1995. So I can't believe it was over 30 years ago. I was working on my master thesis. Anders Lindgren, who studied computer science with me at Uppsala University, as part of his thesis, went in and proposed a soft type system, for Erlang. Simon Marlowe, so the Glasgow Haskell compiler maintainer, was working on his PhD thesis at the University of Glasgow together with Philip Wadler. And they were looking at a subtyping based system. And what the system did is it traded expressive power, for simplicity. So they were going in and trying to understand, how do we get stronger typing in Erlang? Both Anders and Simon met at conferences. They shared a lot of notes and ideas, what worked and what didn't work. But you know what they achieved did not go far and never really made it into production. To quote Joe Armstrong at the time, anyone can write a type system which covers 90% of Erlang, but the remaining 10% is really, really hard. And even the brightest mind in computer science, and here he was referring to Phil Wadler, have struggled. And as a side note, this is because of some of the design choices they made with the Erlang semantics very, very early on. So the tension we were wrestling with, back then is the same tension, we were wrestling with today. So decades might have passed, but those challenges and tensions continued, with Thomas Hart and Joe Armstrong's practical type system, Sven-Olof Nyström's polyvariant soft typing, and Kosti Sagona's Dialyzer. Dialyzer was a pragmatic compromise that admitted it couldn't prove your code was correct, but could reliably tell you when something was definitely wrong. It seems like today we're reaching an inflection point. So Elixir 1.2 is shipping with a gradual set theoretic type system. It's built on years of research by Guillaume, who's on the show with us today. And our second guest, Annette, has been building, the parallel Dialyzer project for Erlang with her team and collaborators. And between them and other projects such as WhatsApp Equalizer, it genuinely feels like the beam is converging on an answer after nearly 30 years. And that's what we're here to dig into today. It's a bit of a long introduction, but there's a lot of history behind us, and it's important to understand the history to understand where we're heading to. So Annette, Guillaume, why don't you introduce yourselves? Welcome to the show.
Hi, Francesco. Great to have us. And we are very happy to be here. My name is Annette Bieniusa. I'm a professor for software technology at the RPTU in Southwest Germany university. And I've been doing research on programming language type systems, distributed systems for almost 2 decades now. And Erlang and Elixir and Beam is one of the core aspects that we deal with in our research, and we also introduce a lot of students to it. So growing the community this way.
Hi, Francesco, Helen, uh, Annette. I'm Guillaume Duboc. I'm a PhD currently at Dashbit. I did my PhD in Paris at the IRIF, it's the Institute for Research in Theoretical Computer Science. And I defended it in January of this year. The title is Typing Dynamic Languages with Set-theoretic Types, the Case of Elixir. And I've been working on type systems since my master's. I did my internship with Giuseppe Castagna at IRIF on the theory of set-theoretic types. So this PhD was an occasion to apply them to real industrial language. And of course, I'm really interested into bringing research to practice. And I was really charmed by this theory of semantic subtyping, set-theoretic types, and really pleased to be able to bring it into practice.
Now, Guillaume, just to kind of start to break the ice and warm you up to the podcast, I'm kind of curious, right? I'm sure you've programmed before. Do you has there ever been a bug that you've introduced to a production system that no type system would have caught?
I don't really have a crispy personal story of a bug, but type systems, I'll take the more general answer to that question is that type systems, they catch a certain given class of bugs, but there are other class of bugs that they just have nothing to tell you about. I'm thinking about, in most cases, non-termination errors. Often the property that we can say after having typed the program is that it's not going to crash, and you know what is the type of the value that is going to compute. But the second thing is that it may diverge, and in that case, you cannot say anything. So it's a bit of an escape, but I've shipped some program that looped because of badly evaluating the where it was going to run out. And otherwise, to take the question more seriously, I think it boils down to how far you're able or willing to go with the complexity of the type system and the amount of work that the programmer is going to have to do. Because a lot of type errors that you don't catch are because the type system has limitations in the expressivity that it is able to describe, or either that or the designers of the type system, they want you to spend a lot of time writing a proof about why your functions are correct. So I would say that I don't wish that I had been given the opportunity to prove that my program was correct every time, because that means sometimes that I would have just spent a lot of time proving that something is correct when I just wanted to scrap it and do things differently in a more simple way.
Now, Annette, what was the first programming language with a type system that made you either fall in love with or have a real maybe disdain for?
So when I learned programming in high school, we started with typed languages, and even in the first university courses, it was Java and Haskell. It was always kind of clear that these languages would have a type system and that types was something that you need to deal with somehow. First time I realized that type systems can actually bring something very, very powerful to the table and help me refine my programs and make them better maintainable and so on was actually a master level seminar where I had to report on the new addition to Java 1.3, namely type variables and parametric polymorphism. And there was, the wildcards and the sub and super type constraints. I realized that type systems can be actually very, very expressive, but it took me a while to wrap my head around it and make use of this expressivity in a good way.
Now, coming back to types, right? I want to start from the absolute bottom on that. If one of our listeners has only ever used a dynamic language such as Python or Elixir, of course, Erlang, how do you explain what a type actually is to them without using the word class and without kind of getting deep and quoting what a textbook would say? And in going on top of that, in Erlang, if you say that a function takes an integer, what is that actually promising when we talk about types within what you're working on?
So from my perspective, types characterize values that are given in a programming language. And if I know that some form of value has a specific type, I know what I can do with this value. So, and this means that when in Erlang or Elixir I have a function that takes an integer, I know that, or I hope that the function will be well behaving whenever I pass an integer to it. And I should not assume that it works correctly if I would pass a Boolean value or another function or something of a different type. And depending on how the type checking is actually done and what the guarantees are that a specific type system gives you, there are certain things that you may assume and that you might not assume. So types, in particular when it comes to functions, can be seen as contracts, as a caller of a function, I can assume a specific behavior if I pass the values according to the type specification, and I can make assumptions again on the values that would be returned.
Erlang and Elixir have always been dynamically typed. Java, Rust, Haskell are statically typed. And people say static catches the bugs before your program runs. Can you tell us what the difference is between static and dynamic typing, and what part of the sentence I just mentioned, basically static catches the bug before they run, is generally true, and what part of that is oversold?
So static and dynamic, first of all, refer to the time when the type check happens, right? Static means it happens before the program gets compiled and before it's executed. Dynamic refers to type checks that happen at runtime while the program is executing. Both approaches catch bugs. For the dynamic, it feels different because very often the program resorts to aborting the execution if a type check kind of fails. And most often this is very annoying, right? So you run your program and then boom, it kind of crashes and you're wondering what's happening. And if the reason is, well, the type kind of goes wrong, then that's really problematic. Yeah. So what you get with static typing is the bugs that actually are the bugs that you can anticipate and prevent them from happening at runtime. What type of bugs can be checked really depends on the type system. So even C that has aspects of a So C has aspects of a static type system, of course. It does not do a lot of dynamic checks. Dynamic checks are somewhat more expensive, right? If you're doing a lot of checks while your program is executing, this will slow the program down. If you compare this to languages that try to provide better guarantees, like Java would still do checks at runtime, like also dynamically check for some aspects that it wouldn't be able to catch during the compilation phase as part of the compilation phase. So checks like null pointer exceptions are actually to some degree can also be considered type checks. And most languages actually use a mix of both. I would kind of claim. In particular, those that have static types will also make use of the types at runtime somehow.
And a lot of developers think static and strong mean the same thing. And they don't. Can you untangle them? Where do Erlang and Elixir actually sit on both axes?
With Erlang, right? Erlang is not statically typed unless you use an external tool, like an additional tool like Dialyzer, say, for example. Then you don't get specific guarantees at compile time or prior to execution. It does checks dynamically at runtime. Whether you consider the type system strong or weak depends a bit on what your expectations are. Erlang actually has dynamic type checks and they give you some guarantees. You can't accidentally rack up your memory.
Annette, a lot of developers think that static and strong mean the same thing when actually they don't. Can you actually start to kind of describe the differences and maybe the positives and negatives of each one?
So static refers actually just to the point in time when the type check is happening. Whether the type system is strong or weak depends on the amount of guarantees or the type of guarantees that you would get with a type checker. Right? You can have very strong dynamic typing, you can have weak static typing, and everything in between. So one thing is not per se better than the other. Even strong type systems can have aspects that make them not nice to use because stronger guarantees typically mean that you need to be more careful in how you write types and how the types look like be more precise, for example.
Guillaume, the phrase that ties this whole episode together is gradual typing. What is it, and why is it the thing that makes typing Elixir possible at all?
I would say that gradual typing is allowing yourself or allowing the type checker to operate with uncertainty about the types. This is the dynamic type or any unknown that you have. And in the case of Elixir, it's quite important because it has been a dynamic language, untyped language for its whole life. So there are entire code bases that exist and that need to work with the new system. you cannot just expect that those code bases are going to have to be entirely annotated with static types before being used again after version 1.21 of Elixir. And so gradual typing allows the type checker to function with the knowledge that, this function here, all that we know about it is that when you give it an integer, it returns you something dynamic, value that you don't know about at compile time. So from a very practical point of view, this is what makes the work possible in the first place. Now, there's another theoretical reason why we also want a gradual system, which is, it is that in the type system that I've designed with Beppe and just Giuseppe and with Jose, we are treating the functional aspect of Elixir. That is, we are typing functions in a very precise way, and case, pattern matching, all of this. And there are some aspects that we have not treated, for instance, typing the messages that are sent. And that means that we need an escape hatch when the type system is not going to be able to give static types to those expressions. And this escape hatch is baked into a gradual system in the form of the dynamic type.
Why is the Elixir team's version of gradual typing different from what TypeScript or Python does today?
The difference is that it is part of its foundation. To design the type system of Elixir, we started from a theory of types that are set-theoretic, meaning that you can express a union of types, intersection. An intersection of two types is going to be all the values that are in both types. Negations as well, all the values that are not in a given static type. So if you get the type not integer is every tuple value, list value, etc. And the dynamic type is also part of that structure. If you do the union of a dynamic type and a static type, what you have is a gradual type. So for instance, you have the type integer or dynamic Boolean. That type is interesting because it tells you how the type checker is going to treat that. It's going to consider that the integer part is a static, so it needs to be handled by a function if you pass this as argument to a function. But the dynamic Boolean part is less strict, less restrictive. So if the function does not handle this Boolean part, then the program may accept this program. That allows us to bake a lot of flexibility into the type system, and I think this is the difference with the way that TypeScript, for instance, was built. Is that at first they introduced I don't. They have two dynamic types. I think it was any. At first, they introduced any as this dynamic unsafe escape hatch, and then they realized that because of the way that they designed the system around it, it was too unsafe and disliked by the programmers who wanted a way to say, okay, I put a dynamic escape hatch, but I want you to remind me that I need to refine it and check it, and this is why after they introduced the unknown. And the reason is that in those cases, the dynamic type is an extra thing on top of type system, and it makes things difficult. At least it makes the design around how it's going to be used non-trivial, and I think that's the main difference.
I mean, the Beam has been around for quite some time, right? Why does it actually need a type system at all, Guillaume?
In in our case, the type system is not going to improve on the runtime because it's really a fantastic runtime. What what we bring, I think, to the table is an improvement on the process of writing a code base or of maintaining a code base. Elixir and Erlang scale to users, but does the code, does Erlang and Elixir code scale to millions of lines of code? And I think that the type system helps with this process because it's going to enable programmers, the senior programmers, to define what the code base is about and have this mechanically checked documentation, and it's going to improve collaboration around the code base. So I would say this is there is an aspect of the type system that maybe can improve the technical aspect of the code, like perhaps improve the quality of the code. Perhaps because the type system is going to guide a programmer towards avoiding some bad patterns, or making sure that, for instance, exceptions are completely handled and well coded. But like good software that has already been written in Elixir Erlang is not going to get better. However, maybe it's going to help writing more of those.
I'd love Annette's view here because, again, Erlang's run telecoms, for 25 years without static types. We're talking GPRS, 3G, 4G, 5G, and Ericsson at Codebeam Stockholm announce, that they're doing all of the 6G with Erlang, 6G Next works with Erlang. You've got pattern matching, you've got supervision free, embracing the whole let it crash approach, and let it crash happens regardless of a type system. So so without static types, the Beam shipped some of the most reliable software ever written, and we're talking a few seconds of downtime per year, including upgrades and maintenance. I want to ask you the obvious question directly: what problems are we actually solving now that we weren't solving in 1995?
So one of the aspects here is that actually type systems catch bugs that are due to programmers that are introduced by programmers, not necessarily by situations that occur at runtime. So let's assume you have a bug that could have been caught by a type system. It might be that you implemented all the supervision trees and everything kind of correctly. So when you hit the specific path, the specific execution path, then your program will, make use of the restart and everything, and it won't necessarily kind of go down immediately. But you have a lot of overhead, and you need to kind of keep in mind that you need to provide supervision trees, etc. And there might be parts in the code where this is not necessarily the case. You don't want to spawn a new process just for executing a function call, making sure that if this function call has a type error, you can kind of catch it somehow. It's also not totally obvious how to deal with this problem at runtime, so you would need to kind of patch the code and so on. And this is all very expensive. And even if a type system just catches, say, 5% of all issues in your code base that happen over the course of the runtime of a system, it's still 5%, right? And this directly reflects in overheads, both on latencies and better machines that you need, and so on, because you need to over provision for these situations. And if it's just a bug that a type system could have caught, why not use the type system to prevent it?
If you try to build the type system you're building now, so this is for Guillaume, in 2005, what would have made it impossible or just not worth the effort?
I think that the immediate difficulty when typing Erlang is that because of the way it is structured around pattern matching, with no need to satisfy a static type checker, you can you can freely have a function that returns an integer or a boolean, and you don't want to build, or rather, you've not been asked to build special type that would encapsulate that, like in the ML family of languages, for instance, where you're going to build a subtype saying, oh, I can have a constructor with an integer under, or another constructor with a boolean under. And so you need your type system to freely represent unions of types, integer or boolean. So you need a fully developed type system that has this property. Another thing is that because you have functions that are able to return those completely different type of values, now it's possible that you're going to do overloading, and that you're going to expect your function to return an integer when given an integer and return a boolean when given a boolean. And that's why you need overloading, function overloading. And you want it baked into your type theory as well, because you want something that follows closely the semantic of the language. And around 2005, there was the thesis of Alain Frisch on Sidious, which showed how you could do this in a language, have function overloading via intersection types and union of types and other very precise features. The theory called the semantic subtyping, but this theory was still missing a lot of things that were developed 10 years after. That is polymorphism, being able to do parametric polymorphism in the context of set-theoretic types was in 2015, and then the ability to integrate dynamic into that was from 2019. So if you wanted to have a theory that easily expresses those free patterns, this very free way of programming that Erlang uses, you couldn't use set-theoretic types in 2005. So you would have to do some very complex inference, some very complex constraint solving. But the way that you present this to the programmer would maybe a bit difficult, because I think that there are two aspects to type system. There's the aspect, is the type system able to represent all the types that you need? Like, is its model complex enough? And is the type system adapted to the way the programmer thinks about the language? And is the type system, or maybe the type language, sufficiently is it easy to understand, right? And I think this is what set-theoretic types bring to the table. There is that we have both a way to technically solve the challenge, and we have a way to present them in an interesting in a sufficiently easy way for the programmers.
Annette, you were workshop chair when, I believe this is pronounced, Kostas Sagodas gave his 15 years of dialyzing retrospective. Now, Dialyzer has been a very good practical answer when we don't have types, right? That it can kind of run through and see if there's any kinds of type issues. I mean, it's really great. It's probably underutilized in terms of not many people using Elixir, at least, are using it. Even people who are using Erlang are definitely not all using it. And its error messages are, infamous in being very, very cryptic. Do you think that Dialyzer was definitely a great step forward in working with a type system and kind of like a good base to work at? Have you used it when you're working on the Dialyzer project, or what do you kind of feel about about Dialyzer?
I typically like to use Dialyzer in my projects, and we always tell the students also to use Dialyzer in their project. projects, there is a catch with Dialyzer. So from my experience, if you use it without knowing what it provides, you get sometimes too high expectations. So being used to static types in the way that, say, Java, for example, provides them, there's a certain class of type errors that I would expect a tool like Dialyzer to catch, but just because Dialyzer has this specific approach of success typing, it will not flag these issues. So this is where people very often get confused. Dialyzer did one decision very great, namely reducing the amount of false positives to 0. So when Dialyzer is complaining, you can be pretty sure that actually there is something wrong with the code. It's not so easy to debug once in a while if you get like several lines of debug output and need to compare very long type annotations or types for functions, say, to figure out in which of the parameter, which option is actually the wrong one. There's been a lot of very nice work from the community and from the OTP team to highlight things and make this more approachable. So this is great. Dialyzer's error messages are going into the right direction. If we can keep the idea of success typing only flagging, not flagging false positives, then we learn something from Dialyzer.
From the Elixir side, is the new type system replacing like Dialyzer's philosophy or building on top of it? And also, where do success typing and gradual set theoretic typing actually agree, and where do they actually start to diverge?
Yeah, the Elixir type system is a replacement to Dialyzer. I would say that previously I was saying there are two aspects to a type system. One is the technical ability of the system to find the bugs, right? And Dialyzer does that very well. And this is something that we've done as well. And I think we are on par with the Dialyzers in terms of bug finding. But the second aspect is the type language and the ability for the programmer to direct the type checker to for the programmer to specify contracts on top of functions and for those contracts to be enforced in a strict way. And this is where Dialyzer is not as convenient as a normal type system, because the way it has been designed is that it sits in the middle of the programs, and it builds this graph of dependency between all the variables, and then it looks at all the checks that are giving some type information, like his integer is going to make variable integer, and then it goes to look for inconsistencies between those. And with the system that we've designed, we are able to have also a top-down approach led by programmers, that when they write a contract integer to integer on top of their function, then the body of this function is going to be the type checker is going to go through it with the assumption that the arguments are integers, and it's going to enforce this in a more strict way. So in terms of user design, it's quite different. I would say that the ability of Dialyzer to find bugs is something we've wanted to conserve. So right now we haven't added the type annotations on top of functions. So we've been working on this type system in complete inference mode or a dynamic mode, and so that means that we've not really allowed the type checker to reject programs. Instead, we've made it give out type warnings. And those type warnings, the philosophy of the current type warnings is that when you get a warning, 90% of the times it is because there is a bug that is definitely going to happen in the same way that Dialyzer does. But in the future, we want to also have the ability for the type checker to say, well, this program doesn't compile well because you told me about its type, and those types are not working out.
Annette, You've worked on CRDTs. We've worked on CRDTs together. You've worked on
Yes.
replication in distributed systems, formal verifications. Types are just one tool in your toolbox, not the whole answer. So taking a step back from that broader vantage point, where do types sit in the stack of things which make the Beam software trustworthy? Are they a floor of a taller building, or are they actually the foundation of that building, doing much more than what its daily users actually realize?
I think there are two aspects to that. So first of all, types help sometimes to restrict behaviors. So if we assume, for example, that a function is only supposed to be working correctly if an integer is passed, then that's an assumption we can make, and we can build arguments and verification toolchains based on these type of guarantees that we get. So my personal take is that we probably, with having the ability to type things, we will enable future verification works that can then build on top of that. And then there's the second aspect, namely that types are really not just for the programmer and for the documentation and so on, but they also have an effect on the runtime. Right now, the type annotations, if I recall correctly, that programmers add to their Erlang code will not, and also for the Elixir code, as far as I know, will not have influence on the execution engine. But in certain parts of the execution engine, types are actually derived and assumed to enable certain optimizations. So these runtime optimizations could be done at a much more greater level if static type information was available, because then we can kind of propagate this information from the code into the compiled version, and then the runtime can make use of it, for example, when allocating space for things or when trying to parallelize things and so on. So they might enable more than the community assumes.
Giuseppe said it plainly at his ElixirConf Europe talk in Malaga. The type systems do not mean error-free. But there's a real risk here. Developers see static types appearing in their language. They get lulled into a false sense of confidence. They start writing less defensive code, fewer supervision trees, and less paranoia about failure. Even scarier, no recovery strategy. These are the very things that make the programming model and the Beam reliable in the first place. Is there concern that this could quietly erode? How do you guard against that culturally and not just technically?
I guess the fear is that programmers will start writing 1,000-line PRs and accept that because it type checks that they can just send it or merge it, and that. But that's also what you want from a good type system. This sense of confidence. All the obvious errors have been tackled, but I think that this problem is in the case of Elixir Erlang, supervision trees, the let it crash philosophy, and all those recovery strategies that give this fantastic uptime. They are not here to guard against type errors. Really, they are here to guard against different kind of errors, like conflicts or synchronization problems, and static types are not going to make people get rid of these. I don't think so. So I think perhaps that is not. It's not the biggest danger there.
We've basically established why why this work matters, what it's not trying to do, of course, what it's trying to do. But let's actually get into the system that Guillaume and his team is working on. What does it look like when it does work, and where do you see like a lot of the strain when it's starting to work?
When the type system starts working, you gain a level of control on your code, which is very satisfying, but also has practical benefits, because you become able to enforce those complex contracts over your code, and that is going to enable you to have for instance, doing refactoring, to have this power at the tip of your fingers, to know that actually you've successfully mutated the way a core function of the logic of your program was working, and that's on top of finding obvious bugs, right? The time where this can become a bit difficult is when the type system is not able to find why your program is actually correct. In a gradual type system, this is a problem, or rather, when you're retrofitting a type system on top of dynamic language, it's a danger, because you're gonna write, good annotation on top of your function, and unfortunately, the type system does not manage to find that in one branch of your program, one of your variables has a type integer. Instead, it thinks it still has type integer or Boolean. And so then you apply this, you do, +1 on this, and it gives you a warning. So this is the lack of precision of the system is, that's why it's extremely important in what we're doing. Because if this happens, then this means that the programmer is going to have to relax the safety that is expected of his function. For instance, you can wrap the input of your function in dynamic. So you say, okay, I was writing the annotation that my function receives an integer or Boolean and then does whatever. Instead, they can wrap it and say this is a dynamic integer or Boolean. Both of those are dynamic. And this is going to relax the system, so that now if this input is used as a list, you get an error. But now if it's used only as an integer, then the system is going to load this because it sees that it could be an integer at some point. So I think when you start having to play with the limits of what the type system can express, this is the difficulty. And in that case, we're going to have to either provide clear warnings explaining, oh, well, this is a known limitation of the system. You could perhaps try to rewrite this in this way, rewrite it in that way. But it's not obvious that we can think of all the possible cases in which this could fail. And otherwise, this is the reason why the way the type system works has to be very well explained and understood by the programmer, so that they can understand what's going wrong in a given situation. And it is better that the system is easy to understand, so that they can think, oh, well, the system works that way and that way. So in this case, it's not going to be able to type my program. So I'm going to have to do it another way because of those reasons. I hope we've minimized those instances, but they're going to exist.
I'd like to go over one of the examples that Jose used in this talk before. It's a very simple function. Basically, it's a function that takes in a string that splits on commas, and then have basically a list with different size strings, and it returns the largest string of those. Now, can we talk a little bit more about this in regards to the type system? Because if you think about it, what happens when you pass in an empty list? What happens if you pass in, like a string that doesn't have any commas? If you just pass in, something that does have lots of commas, but maybe like nothing in between? How would the type system kind of help with this problem? Or do we have to kind of use you talked about kind of like an escape hatch with dynamic, right? Would we need to rely on something like that?
When it comes to very precise behavior, I don't know, for instance, imagine a program that works all lists except lists of size 3. And in that case, it's going to crash. Well, there are two ways. Either you want your type system to be able to do this precise reasoning about the size of lists, or you don't. And if you don't, then an easy way is that indeed you're going to work with a dynamic list. And all you're going to want from your type system is that you want it to check that, okay, I'm passing a list through my programs and not a tuple and not not a struct. And that's what you're expecting from your type system. You're not expecting your system to count the size of lists for you, and you're not expecting it to do all of this. And if you actually do want the type system to handle this kind of things, then sometimes it can mean that you're going to have to do a lot of work. It's not necessarily that we can't express those things. We can actually, in the theory of set-theoretic types, express a list of a given size, or express very precise integers, the type of integers that are between 2 and 5. But the thing is that if you have this precision and you want to use it, then you're starting not to write types, you're starting to write equations. Like you want to ensure that after this plus operation, then your function is going to indeed have the list of size 3. And the type checker can help you, but I think it stops at some point when you think that perhaps if you're doing this very precise thing, you're not writing. It's not something that's important to the core logic of your program.
José's talk laid out an argument that I want to test with both of you. Simple type systems are easy to learn, easy to write signatures for, they're fast to compile, but they force you to push invariants to runtime. Expressive type systems will catch more, but the signatures explode in complexity. Error messages get worse and compile times suffer. He called it an inherent trade-off with no silver bullet. Guillaume, where did the Elixir team choose to sit on that spectrum, and what made that the right point, and the right approach?
I think that the big challenge in this work is that we're trying to answer the question: is a type system based on semantic subtyping, set-theoretic types, or which is founded on that theory? Is it correct? Is it the right point in the design space for programmers? And this is the exact thing that is a danger, is that we are so precise that the errors that are given or the types that are inferred for functions, they become too hard to handle. And I think we are sitting right at the point where it's good to understand. It's easy to understand. I think the notion that a type is either one or the other, or both, is enough to present. And in order to reduce the complexity, we've made some choices to limit the representation of types. Those are choices that have been done for now, so they could potentially be changed. But for instance, we're not having precise singleton integers, because then you could express a union of the integers between -10 and -5 and 5 and 15, and have this whole machinery on integers. And this may be not a part of the language that is required. We have atom singletons, so they are able to express the way in which Elixir really uses those a lot to have target tuples. So we're trying to find the correct, the simple enough place where we can say that the system is both precise and still understandable by programmers. But this is a constant effort, I think. There are some there have been some bugs reported as issues in the in the compiler before that, where it was just a giant union, which this was because we weren't simplifying, of course, but seeing the type checker produce a giant type is one of my personal fears, I would say.
Annette, you're building Dialyzer for Erlang on the same theoretical foundation, but with different design priorities. Do you land at the same point on that spectrum, or somewhere different? And if different, why?
We land at a slightly related point, but not exactly the same point. When designing Dialyzer, we made a very conscious decision to keep the type specs as Erlang code and also Elixir code still has, right? So our assumption was that programmers can use with the type language, with the type specification annotations that come with the Erlang standard, that these are the tools that allow them already nowadays to express what their functions, for example, are supposed to do. And we didn't want to have too many moving parts, so this was kind of the assumptions. Let's try to take code with its type annotations as it is and see how far we get. It turned out that unions, intersections are pretty important, but even numbers like the union, the singleton types Guillaume just mentioned, do occur. So like in the standard library, there are, I think, something like a couple of hundred annotations where we rely on these singleton types. And the question is, do we want to deviate from that or not? Our decision was to stay with it. Other than that, the set-theoretic types turned out to be, I think, the right theoretical foundation for approaching this type checking for the Beam languages.
Both type checkers have gradual typing on top. Why does set-theoretic typing buy you? What does set-theoretic typing buy you that you couldn't have gotten from a more traditional type system?
So for me, it's really this combination of this different expressiveness that you get with union type, with intersection types, and also with singleton types, for example, for the atoms. Gradual typing is, as Guillaume mentioned, is required to help programmers and not require them to annotate every single line or every single function in a module with a type and be overly precise when it's not needed, right? So gradual typing is for practical reasons, I think, unavoidable. The combination of different aspects that you can have with set-theoretic types makes them very, very powerful. And they're also a good mental model for describing values in the language.
Intersection and unions, they are the user-facing types, but there is also differences that are expressible using set-theoretic types. And they have particularly important value on the technical aspect of checking programs, because they allow you to precisely analyze pattern matching. So you have different clauses and they do pattern matching, and you're able to compute the type of the first clause. And in the second clause, you know that the type of values that enter this second clause, it's all the ones accepted by the pattern minus the ones accepted by the first clause. And this difference, we're able to express it at the type level, and this gives us a lot of precision. It allows us to give exhaustivity warning, or it allows us to detect branches that are never going to run because all the values were already coded by previous clauses. And so it is not necessarily very present in annotations, although it can definitely. But from the technical point of thing, it's really important, and it's I think it's also one of the less. It's something that does not exist in other languages that have introduced ways to do unions and sometimes intersections in a bit of an ad hoc way.
So you both mentioned process boundaries as one of the hard problems. And that's where I want to take the conversation next. That's where Alan and I want to take the conversation next, because the Beam's whole identity is built on process and message passing. And I suspect that is your territory.
Everything we've talked about so far happens inside of a single process. Now, the moment that a message crosses a process boundary, or worse, a network boundary to another node, what changes for the type system, and what does it stop being able to tell you?
So this is for us typically the boundary where you have to switch, or where you typically would switch to dynamic, because you don't exactly know what type of message to expect. There are type systems that deal with these aspects, that try to approach typing of mailboxes, for example. There's very recently a line of work on mailbox types that one of our students here is looking at. There are session types that help in dealing with understanding what type of messages are passed between processes as part of a protocol. We started integrating some of these ideas, so kind of a poor man's approach for mailbox types, if you wanted to say so. This is ongoing work, and we are able to kind of make some progress on that, but there are inherently some limitations. Yeah, so if your message can deal, if your receive can deal with a lot of different type of messages, and you don't know what you get, you lose preciseness at some point.
Let's set aside what's pragmatic to ship this year. 10 years out, what do you personally hope the beam looks like? So effect, session types, dependent types, deeper verification, or something new, which has not been named yet. Which of these, if any, do you actually expect to arrive? So let's start with Annette first.
My personal guess is that we will see more work towards deeper verification approaches, just because generating code becomes much simpler. We can have a large number of modules, generated without completely understanding what they do. So supporting programmers in getting confident about their code is, I think, the most important thing that we need to address in programming languages in the next couple of years. And verification is, in its very many different forms, will be exactly this. If we have good tools that help us verify behavior, we can be sure that the code actually does accordingly.
My answer is similar to Annette. I think that a fantastic state would be that the type system evolves and becomes able to serve as infrastructures for more complex techniques. So I could imagine, for instance, that you have a light typing mode for a program that finds common type errors, and that you can at some point mark that there is going to that the proof for some function, for instance, that this function's logic is correct because it's implementing sorting, and you want to know that the sorting is going to be correct, that this is then delegated to some other tool that provides deeper verification. Ideally, I think that type system is made to be nice to deal with from the programmer point of view. So ideally, you would use the type system and then delegate, but your main interface would be the type system for those deeper processes. I think also one very interesting question for me is what is the good way to bring these more complex ways to deal with sending messages and all of this. For instance, session types are a thing in the theory of typing concurrency, and the question is what form would it take to bring these verification techniques to language as Elixir, which would it take the form of annotations? Would it be simple enough to understand? And would it bring? Would it cover the use case that people need? Right.
Very quickly, right? If we were to kind of sum up this whole conversation and what you've learned, what's one thing that you wished every Beam developer understood about types, and one thing you wish that every type system researcher could understand about the Beam? Let's go to Annette first.
Types don't hurt. There is a certain learning curve, but there's a lot of things that you actually get from it. So trying to hit the sweet spot between too much work on the type annotations and the nice guarantees and the confidence in the work that you get. I think this is something that I would hope for many programmers that are now refraining from using types because they seem too complex or complicated. It's not as bad as it might seem to be, right?
That The point of a set-theoretic type system for the beam is to catch the one path out of 100 that is going to fail because this struct at this point, or this map at this point, does not have the given field anymore. And so what we are helping with is the really edge cases, those things that even a very well designed library and a very well designed project is going to have struggles with. And this is rather than promising a fight against a very complex logic design to make sure you don't write bad code. I think this is the interest of types for the beam. And you said, I think, what should researchers understand about the beam? For me, what I understood is that the beam is stronger than me, and the runtime at the importance of the quality of the runtime is something that is it's the first it's the main point of a language, and the role of a type system is to support that from, rather than restrict it. And if you have a runtime that is so excellent that you can afford to program in a dynamic way with a pattern matching or by having a message passing or having all those extremely dynamic, very hard to type features that Elixir or Erlang have, then the role of the type system is going to get on their level.
The Beam ecosystem is actually great for research. Yeah, we have real-world problems that have a high impact. We have a long-standing community, and the languages are very active, right? So the community is active, the languages are evolving. There is no need to assume that the Beam is obsolete in any way. I would rather claim it's getting more and more important with every cloud server that runs some Erlang or Elixir code, right? And there's a great opportunity to make a point and have impact with the research that you do.
So Annette, Guillaume, thank you both. This has been exactly the conversation I was hoping for. We've got two amazing researchers from sister projects who've spent years thinking hard about the same problem, but from different angles. And what I'm personally taking away from the last hour, I hope the listeners too, is that the type system arriving in Elixir 1.2 isn't the end of a 30-year argument about typing on the beam. It's actually the moment that argument finally has the theoretical foundations and the engineering pragmatism to move forward together. So if you want to be part of where this goes next, the most useful thing you can do this week is to try Elixir 1.2 release candidate, read Annette's, same but different paper to understand the broader landscape and report back what works and what doesn't. I think both teams generally want the feedback. So, thank you so much for listening. Don't forget to subscribe. And for the record, this podcast was recorded on May 28th, 2026.